Welcome to Mastering Solutions. We have the same figure in this question, and we're told that we have a wavelength of 600 nanometers this time. 600 times 10 to the negative 9 meters. The slit width, in this case, is a single slit, so that will be A, and that is 0.15 millimeters, so that's times 10 to the negative 3 meters. We need to figure out the distance from the slit to the screen. So that's going to be L. That's what we're trying to solve for. We also need to figure out what is Y in this case. Y is going to be the distance from the central max out to the first minima. Because remember, for the single slit problems, we're dealing with minima, which is P. And so if we're going to use the Y for this one right here, then we can use a P of 1. If we use from this spot out to this one, then a P, of course, would be 2. So we'll use P of 1. And since this whole space right here is 1 centimeter, from the center out obviously is just a half. So we have 0.5 centimeters, or 10 to the negative 2 meters. Now we have all the variables that we need, because the equation that we're using, of course, is Y is equal to P lambda L over A, but we need to isolate it for L. So let's times both sides by A, and then we'll divide both sides by P lambda. So now that will give us L is equal to Y times A over P lambda. So now we have everything that we need. We have our equation isolated for what we're trying to solve for, so let's plug it in. So L is equal to Y, which we said is 0.5 times 10 to the negative 2 meters. A is 0.15 times 10 to the negative 3 meters for the slit width and the single slit. And then that's over P, which we said is 1, and lambda is 600 times 10 to the negative 9 meters. So we have 0.5 times 10 to the negative 2, and then that's times 0.15 times 10 to the negative 3. All that gets divided by 600 times 10 to the negative 9. So our answer in this case is 1.25. So we could round that to 1.3. So the distance from the single slit out to the grating is 1.3 meters.